Hello guys, welcome to the Innovation Lab. In this video, we're going to be conducting the initial power on testing on our high power DC to DC boost converter prototype design. Also guys, the goal of this video is really to share the progress that we have made on this design with you guys. So in this video, we're going to be going over the design schematic so that you guys can follow along with what we're doing. Also in this video, I'm going to be introducing our power inductor design tool that we put together to help you guys design your own power inductor. Alright guys, but before we get to all the wonderful testing and amazing detail that we're hoping to share with you guys in this video, let's go ahead and first of all assemble the converter board, then we'll come right back into it. Alright my friends, let's get started. Alright guys, so the goal of this video is really to share the progress that we have made with you guys. This is in no way a perfect design. Actually, this is the first pass of the prototyping effort. This is more like a schematic verification board, not even a high power board. We don't have any stitching on the layout as you guys can see here. So we don't expect to push a lot of power through this board at this phase. Alright guys, so this video is not sponsored, but I wanted to give a quick shout out to Next PCB for the awesome job that they did. They have a cool process for ordering all your boards, so you guys are welcome to go check them out for your PCB fabs. Also guys, we recently became a member of the Amazon affiliate program. So what that means for you guys is that in every video that we make, we're gonna add a kind of a bill of materials in the description, anything that you can buy for cheap on Amazon. Honestly, that will go a long way in helping the Innovation Lab, because anytime you guys place an order using those links, we will make a small commission, and all that commission will go back into buying all the necessary components and materials that we need to make all these awesome videos for you guys, and also build all these projects. So the truth is that we're getting a lot of offers for sponsorships, which we really appreciate, but we are not really ready to get into that for now. So we just want to focus on the projects, focus on growing the channel, and all of that can come later. Alright guys, so let's go ahead and look at what we have on our test setup for the initial power on testing for this converter. So that will be actually the official power on testing for you guys. So we have our converter here, of course, but then looking from left to right, we have our 36 volt power supply. So for testing like this, I prefer to use these power supplies and not battery systems, because these power supplies are kind of smart. So if I have a short or a failure on the converter, that will kind of present a short at the input of the converter. What will happen is that the power supplies will trip. But in the case of using a battery, because the battery is not really a smart power supply, so what will happen is that you're going to overload your converter and your fuse will blow. All right, so going from there, we have our input current probe here and our input DMM to show us the input voltage and input current. And on the output side, we have our fluke DMM and our current probe here to show us current measurements as well. And here we have our oscilloscope, and we're going to be using it to kind of keep an eye on the PWM drive signal that we're sending to the power MOSFET on the converter. Alright guys, the initial test that we're going to conduct on this will be the output voltage test, and we really want to push the limit of the output of the converter. My goal is to get to about 150 volts DC, and after that we're going to bring it back down to kind of conduct our initial phase of the load testing at a lower voltage. Alright, so let's go ahead and turn on the system. Alright, we are seeing the PWM signals on the oscilloscope. Over here we are seeing 90 volts on the output. So we kind of started at 90 volts because I really want to push the output to the limit. We can make some changes in the design to make sure that the converter will start at a lower voltage, then we can dial it up as needed. So we can easily make that change by adjusting the resistor network that we use on the feedback loop, as you guys can see here. And I'll cover that later when we go to the schematic review. Alright, so now adjusting this potentiometer counterclockwise actually increases the output voltage the way I have the board laid out. Alright, so let's keep an eye on the output DMM to see what's happening. As you guys can see, we get to 150 volts DC, and this is amazing. And I believe we can actually go higher than that if we wanted to, because the MOSFET that I'm using has a high enough VDS rating to allow us to go up to 200 volts. But for the purpose of this initial testing, I'm just going to keep it at 150 volts DC. Yeah, as you guys can see, we have 36.9 volts coming in at the input of the converter, and we are seeing 150.5 volts ready to go to our load. But we're not going to use this voltage for our load testing. Alright guys, the goal of the initial load testing was really to apply a small load at the output of the converter. Then we enable the boost mode by enabling the PWM drive signals that goes to the MOSFET. Basically, we want to see how the converter will wake up with that amount of load applied. As you guys can see here, what we did was to set the output voltage to about 125 volts. So overall, what we saw was that with about 300 watts of load applied at the output, the voltage dropped down to about 120 volts. And when we look at the efficiency comparing the input power versus the output power, we got about 92.4% efficiency. At this stage, I don't think that is the best, but also it's not too bad. For the second phase of the load testing, the goal was to use our DIY Arduino load control module that we have here to incrementally step in the load. And with this, as you guys can see, we were able to apply a total load of 674.8 watts at the output of the converter. And that was at a delivered output current of about 5.6 amps. Looking at the input, we were actually able to use this configuration to push in about 21.19 amps going into the converter. So this means that when we do the math, we got to an efficiency of about 87.5%. And again, this is not the best. This is not the ideal efficiency that I would like to get to. Again, guys, this is just the initial testing that we're conducting on the converter. And lastly, one thing that I observed on this converter as I increased the amount of load I have at output was that I was kind of seeing a lot of noise on the system. And this was because at this stage, this board is not really designed to handle this much current flowing through it. To be able to handle that much power or that much current going through the board without generating some unwanted EMI noise, I will have to redesign the PCB layout. So essentially what we need to do is to apply some stitching on the power traces, and also we have to modify a few things on the layout to help us lower the parasitic inductance and capacitance that we are seeing on the board. Alright guys, I know that a lot of you guys have been asking for us to show you guys the input and output response of the converter, especially under load. So what we have done is to add a couple more tests to go over that. So the first test we conducted was to measure the input and output ripple of the converter under load. And given that our scope here is a 2-channel scope, we were able to connect the input of the converter to channel number 1 and the output of the converter connected to channel number 2. And we conducted the test with the scope set at 20 megahertz bandwidth. So looking at our measurements, what we saw at the output side of the converter was a 10 volt peak-to-peak maximum and an RMS value of 600 millivolts. So at 120 volts DC output, 10 volts peak to peak puts us at about 8% ripple. And in my opinion, I think that's a little bit high. On the input side, we saw a 5 volt peak to peak maximum at an RMS of 500 millivolts. So going forward, we need to be able to fine tune the PCB layout and the design to be able to knock all of this noise down to an acceptable level. Alright guys, the second test we conducted was a step response of the converter. Essentially what we're looking for here is to step in a load and to see how the output of the converter, control loop, voltage feedback, the current feedback, how they're going to respond in regulating the output of the converter. So what we did for that was that we set the output voltage to 126 volts. So we set a falling edge scope trigger at 122 volts. And the goal is really to monitor what is going to happen at the output, which is channel number 2. Alright, so what we saw with all these settings was that we were able to get our scope to trigger at an applied load or stepped load of 260 watts. And that means that our output voltage dropped down to 120 volts from 126 volts. That also means that we saw a voltage drop of 6 volts. Alright guys, is this perfect? No, it's not perfect. There's still a lot of work to be done, but at least my goal was to make sure that we stay as close to 120 volts as possible. And at this stage, looking that this is still a breadboard, I would say that I'm happy with that and I will call that a success. Alright guys, before we get into the actual design schematic, so let's go over the design topology of this boost converter. The first thing we have here is our input power. So this design can handle an input voltage range of 12 to 36 volts, and we have two voltage regulators that provide power to the MOSFET driver and the PWM chip. We have a 10 volt regulator that provides power to the PWM chip, and the 12 volt regulator that provides power to the MOSFET driver. Then after that, we have our output power section, as you guys can see here. And this is where you have the power inductor, the drive MOSFET, you have the rectifier diodes, and the output filter cap. Yeah, so essentially with the boost converter working, provides power to the load, and we use the current sense resistors to sense how much current the load is driving, and all of that information now gets fed back to the controller. The output voltage control of the converter is handled through the voltage feedback loop, and the output current control of the converter is also handled through the current feedback loop, which all goes back to the PWM controller, the TL494 that we're going to be using. Alright guys, for the schematic overview, we will start by looking at the actual internal structure of the TL494 PWM controller. So this controller has a breakdown of all the internal components that are tied to all the respective pins. So what we have here is that RT and CT, which are tied to pins number 6 and number 5, are connected to an internal oscillator. So when we put a resistor value here and the capacitor value here, it actually helps us set the switching frequency of the PWM chip. Pin number 4 is where you have all the voltage comparators that is used for dead time control. Connected to 1 and 2 are the error amplifier that handles output voltage regulation. Connected to pins 16 and 15 is the second error amplifier that handles the output current regulation. All right, then looking over here too, as you guys can see, we have VCC coming in at pin 12, and we have an internal reference regulator which delivers an output voltage of 5 volts that you can use to implement other functions that are external to the TL494 chip. Also, we have two internal transistors that actually is used to deliver the output PWM signals. So 8 and 11, as you guys can see, is the open collector that goes to the transistor, and 9 and 10 is your emitter. Alright guys, so this is the page 1 of the schematic, and this is the input power section. So as you guys can see here, we have our input power connectors, and we have our input fuses, input filter caps, and these are the regulators that I was talking about. This is our 12 volt regulator, and this here is our 10 volt regulator, and we added some resistors here to be able to allow the input voltage range to expand up to 36 volts. The idea is that once we have a load on the system pulling power from the regulator, we'll get a little bit of a voltage drop at this node right here. And this is the actual design schematic. I did my best to simplify it. So as you guys can see right here, I guess we can start from the top. So here is our MOSFET driver, the DC4420. And down here is our PWM controller, the TL494. We have two MOSFETs here that is being driven by the MOSFET driver. And this is our power inductor. This is our rectifier diodes, output filter capacitors, and this is our current sense shunt here. These connectors here will be our output power connectors. All right, so we talked about feedback loops. So this where it says V adjust is our voltage feedback loop, and basically all it does is to send the voltage feedback signal to pin 1, which is the non-inverting input to the first error amplifier. And the current feedback loop, as you guys can see here, where it says I adjust. So this loop here goes back to pin 16, which is again the non-inverting input to the second error amplifier that regulates the output current of the converter. I added a boost enable switch here. When you power on the system, if your input voltage is 36 volts, you're going to be getting 36 volts at the output. If it is 12 volts, you're going to be getting 12 volts at the output. But once you enable the PWM signals by turning on the boost enable switch here, then your output voltage will jump up to whatever you have set it to. In a nutshell, I can really go in depth, but we may not have enough time to dig into the design here. All I can say is that I have been able to test the circuit. It works well. This is kind of the bare bones of the design. My plan is to add more protective functions or features to this design as we go forward, but I am more than happy to share this with you guys so that you guys can get creative with the design and as I take my time to modify the design that we're going to eventually call the product of the Innovation Lab. I think I have full confidence with this design that if you guys follow this design, follow this schematic exactly how it is, you should be able to build yourself a good and well-functioning DC to DC boost converter. So for the power inductor for this design, what I'm using is a 40 microhenry inductor. And after this, we're going to glance over the inductor design tool that I put together. I am still modifying it, but I'll show you guys how I was able to come up with inductance range of within 30 to 40 microhenries. Yeah, I hope you guys can follow this schematic and make it work for you. Alright guys, so I'm currently working on this design tool. So basically this is an Excel calculator that I'm putting together, and my plan is to kind of automate all the different calculations that we consider when designing a converter: MOSFET selection, inductor selection, input capacitance, output diodes, all that good stuff. But it's still a work in progress. I think we have the inductor selection dialed in. So what I did was that I found this really nice white paper from Texas Instruments that gave some guidance on how to select inductors for your boost converters, essentially using this formula right here. So what I did was to build that formula into our spreadsheet, as you guys can see here. All we really have to do is to put in the design variables, and it will kind of give us an estimated inductance value. So as you guys can see here, say we have input voltage, output voltage, maximum output current, and switching frequency, percentage ripple. The percentage ripple we have to calculate, and there is a recommendation again on that white paper that you should really account for about a 20% ripple current. So that's why I'm using 20% here. So our design is going to use 36 volts input maximum and an output maximum. I said I want to design 120 volts, an input current of 20 amps, switching frequency of 47 kilohertz, percentage ripple inductor current of 20. So now let's look at what's going to happen if I try to change any of these values. If we increase the maximum input voltage to about 60 volts, now it's telling us that we need to design almost an 80 microhenry inductor. So let's put it back down to 36 volts, back to the original value. The next variable is the maximum output voltage. So let's say we want to design this to a maximum output voltage of 80 volts. Now it's telling us that we need a 47 microhenry inductor. All right. And when I finish the fine tuning of this tool, I'm going to be able to put it on the website also with the schematic so that you guys can download it and use it as you're doing your designs. But just like every other thing, I need to be able to test it first so that, I'm not giving you guys the wrong tool. Let's do one more exercise. So if we change the maximum output current, let's say we choose 60 amps. Now it's telling us that we need a 13 microhenry inductor. So yeah, and I've been able to kind of play with this as I'm trying different inductors. It actually quite works, which is really amazing. All the inductors that we're building, we're not just winding copper wires together. We actually follow in some design rules and some design formulas. We're looking at a whole bunch of things that is guiding us through the process. And I'm sharing all of this with you guys, and I hope that you guys find them helpful. Alright guys, we really have to end the video here. Thank you for making it to this point. My goal was really to adhere to a time budget of 25 minutes. And as you guys have seen, yes, the converter is not perfect, but we have been able to use this initial breadboard to implement some cuts and jumpers to give us a working schematic. And we also presented the schematic to you guys, and we went over the inductor design tool, and we're going to be making more changes and adding more components to the design. And if you would like to see all of that, don't forget to subscribe to the Innovation Lab. All right, my friends, I will see you guys in the next video.